Welcome to Dr. Sherry's Astronomy channel. The theme this time is, first detection of light emitted from inside a black hole's entry region. A black hole is a celestial object in space with such strong gravity that not even light can escape it. Nowadays, black holes are well known, and almost everyone recognizes the name. However, observational evidence for their existence was first established in the 1960s with the advent of X-ray astronomy. The initial discovery of Cygnus X1 marked the beginning of numerous X-ray observations aimed at unraveling the mysteries of black holes. This is because, as a black hole consumes surrounding material, it forms an accretion disk. The accretion disk becomes extremely hot and emits X-rays. This kind of conceptual image, often seen in binary systems of a black hole and an ordinary star, has been constructed through years of X-ray and other observational studies. When viewed in such illustrations, the spatial structure is clear, but in actual observations, black holes appear as mere points of light. Researchers rely on spectra and time variations as clues. For instance, the X-ray spectrum of a black hole binary observed by Japan's Asuka satellite appears as follows. The horizontal axis represents energy, while the vertical axis represents brightness. The black line is the data, and the blue dashed line represents a model of light emitted from the accretion disk at various temperatures. The accretion disk spans a wide area, with its temperature varying according to the depth of the gravitational potential. As a result, the spectrum is not a simple blackbody radiation at a single temperature but rather a composite of blackbody radiation at various temperatures. Moreover, the actual data reveals an additional component known as the hard tail, whose origin remains unclear. This spectrum may stem from jets or could hint at unknown physics related to black holes. The accretion disk formed around a black hole is thought to be heavily influenced by the black hole's mass and spin. Observing the accretion disk allows researchers to estimate the physical properties of the black hole. In classical mechanics, stable circular motion is possible at any radius within a spherically symmetric gravitational field. However, in the case of a black hole with its immense gravitational pull, Einstein's theory of relativity must be applied. In this scenario, stable circular motion becomes impossible as one approaches the black hole, with the innermost stable orbit termed the innermost stable circular orbit, ISCO. In other words, material cannot maintain stable rotational motion and cannot exist as an accretion disk inside the ISCO. The radius of the ISCO is thought to vary depending on the black hole's spin and the direction of the accretion disk's rotation. When the black hole and the disk rotate in the same direction, the ISCO radius becomes smaller. When they rotate in opposite directions, the radius grows larger. The predicted relationship is as follows. The horizontal axis represents the absolute value of the spin, while the vertical axis represents the radius, normalized by the Schwarzschild radius. A spin value of 0 indicates no rotation, while a value of 1 corresponds to rotation at the speed of light. For prograde, same direction, rotation, faster spins result in a smaller ISCO radius, moving closer to the event horizon, the boundary beyond which even light cannot escape. If this prediction is correct, as the spin approaches the speed of light, a gap would form between the ISCO and the event horizon. Earlier, the X-ray spectra we examined modeled light emitted only from the stable material orbiting outside the ISCO. In other words, previous analyses considered only light emitted by matter in stable rotation around the black hole, disregarding emissions from material plunging into the black hole beyond the ISCO. Recent advances in supercomputing have made it possible to theoretically simulate the behavior of matter within the ISCO. This diagram illustrates the speed of the material, with red indicating higher velocities. The inner dashed black line marks the event horizon, while the outer dashed black line indicates the ISCO. Inside the ISCO, material is seen plunging toward the black hole. Surprisingly, these theoretical simulations revealed that material inside the ISCO emits light as it plunges toward the black hole. This light includes thermal radiation similar to blackbody emission and non-thermal radiation. The predicted spectrum looks like this. The horizontal axis represents energy, and the vertical axis shows brightness. The yellow dashed line models the spectrum of light emitted from within the ESCO, combining thermal blackbody-like radiation and a power law-shaped non-thermal radiation. The upper panel represents a spin of 0.9, and the lower panel a spin of 0.7. Comparing these predicted spectra with actual X-ray observations shows similarities in their shapes. However, producing non-thermal radiation requires extreme parameters. As theoretical models advance, applying them to actual data becomes crucial. Dr. Andrew Mummery and his team at Oxford University tested these models against observational data. The target object was MAXI J1820+070, a black hole X-ray binary. This celestial body was discovered on March 11, 2018, by MAXI, an all-sky X-ray monitoring instrument on the International Space Station. Following its discovery, numerous telescopes conducted follow-up observations, revealing that it lies 10,000 light-years away in the Milky Way. Its binary companion is a star 8 times the mass of the Sun. High-resolution X-ray images from NASA's Chandra satellite show it as a point source, while radio observations confirm the presence of jets emanating in both directions. One of these jets appears to move at 1.6 times the speed of light, a phenomenon characteristic of high-energy astrophysical systems such as black holes. The research team focused on data from NASA's NuSTAR satellite and the NICER instrument aboard the International Space Station. NuSTAR is the first telescope capable of focusing on hard X-rays above 10 keV, covering a range from 3 to 80 keV. NICER, with its 56 X-ray telescopes, captures high-quality spectra with short time intervals. Combining these observations allowed for precise monitoring of X-ray variations and spectra around the black hole. The observed spectra are shown here. The horizontal axis represents X-ray energy, and the vertical axis shows brightness. The black points are data from NICER, and the purple points are from NuSTAR. Combining data from these two instruments provides a highly detailed spectrum of the black hole binary. However, examining the spectra alone does not reveal whether light originates from within the ESCO. First, the team tested whether the spectra could be explained solely by emissions from the outer accretion disk and hard tail. The results are as follows. The upper panel shows the actual spectrum, while the lower panel displays the model-to-data ratio. A value of 1 indicates that the theoretical model matches the data. The green line represents a model of combined blackbody emissions from the outer accretion disk, while the red line represents a hardtail model. Blue indicates the sum of these two components. The results show significant discrepancies, particularly around 8 keV, demonstrating that the accretion disk alone cannot explain the data. Next, the team incorporated emissions from within the ESCO into the model. The green line now includes these emissions, while the red line remains the hardtail. Blue represents their sum. This updated model significantly improves the fit around 8 keV, confirming the presence of light emitted by gas plunging into the black hole. To facilitate similar analyses for other black hole binaries, the research team has released user-friendly models for spectral analysis. Applying this method to a large number of black hole binaries is expected to advance our understanding of spacetime near the event horizon. Thank you for watching, and I'll see you in the next video. If you enjoyed this video, please don't forget to give it a thumbs up. Hit the subscribe button and the notification bell icon, so you'll be notified when new videos are released.